All right, this is find the average acceleration. A calculator problem. Is it a calculator problem? No. No, I meant non-calculator. Yeah, I don't see any decimals on this at all. Yeah, no decimals. Non-calculator. Let me change this real quick. Non-calculator. All right, here we go. Train A runs back and forth on east-west section of railroad track. This is charts, by the way. Train A's velocity measured in meters per minute is given by a differentiable function, v sub a of t, where time t is measured in minutes. Selected values for v of a of t are given in the table above. So we have velocity at a certain time is what's in the chart. A, find the average acceleration of train A over the interval 2 to 8. Well, if we want average rate of change, we do S of B minus S of A over B minus A, and S being position. So if you wanted average velocity, then you would do slope, and that's the slope of the secant line. Well, here we want average acceleration, and we have velocity. So we want V sub A of 8 minus V sub A of 2 over 8 minus 2. So that actually gives you average velocity. You have to use, or excuse me, average acceleration. Well, that's negative 120 minus 100 over 8 minus 2. So negative 220 over 6, that's negative 110 over 3. And I suppose we probably need a label for this. We're going to go meters per minute squared. Meters per minute squared, because that's acceleration. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t with 5 to 8? Give a reason for your answer. Well, we have V sub A of 5 is equal to 40, which is greater than negative 100. And V sub A of 8 is equal to negative 120, which is less than negative 100. Now, velocity is a continuous function. So this is continuous and differentiable. Then we can say that there exists some t that such that, how do we go, such that V sub A of t is equal to negative 100 by the intermediate value theorem. So the intermediate value theorem says that if you have a continuous differentiable function, then all values will be possible in between those two values. So from negative 120 to 40, all values will be taken on. So somewhere there's a t that'll give negative 100. At time t equals 2, train A's position is 300 meters east of the origin station. And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. Then use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equals 12. All right, so that's a mouthful. At time t equals 2, trains A position is 300 meters east, and the train is moving. So write an expression involving an integral that gives the position of train A. Well, at t equals 2, we're at position 300. And then if we add on the integral from that spot, from 2 to 12 of v sub a of t dt, that gives us the position, because it's position plus displacement equals new position. So the integral is the displacement. Now we want to, they're asking us to use a trapezoidal sum to come up with that displacement. We're going from 2 to 12. So there's the first trapezoid, second trapezoid, there's the 3 trapezoids right there. So now the area of a trapezoid is 1/2 times the height. And the height in this case is 2 to 5, that's 3. and then base 1 is 100, and base 2 is 40. So there's the first trapezoid. Plus 1/2 times 5 to 8 is 3, and we have 40 minus 120. And then plus 1/2 times 4, negative 120, I'm running out of room, minus 150. And I probably should have put this down here because I need a little more room. Should have put that down here. So we have 300 plus, let's see, half of 140 is 70. 70 times 3, or yeah, times 3 is 210. 210. Negative 80, half of negative 80 is negative 40, so I'm looking at minus 120. Oh boy, I can't even read my own handwriting here. Let's do this. Times 4 times negative 270. So we got some work to do here. 510. 2 times negative 270. How about we do it like that? What's this? 390? 390 minus 540. Negative 150. Got it. Eventually. Negative 150 what? Negative 150 meters. D. A second train, train B, travels north from the origin station. At time t, the velocity of train B is given by, that's the velocity. So we have a chart for A, we have an equation for B. And at time t, the train is 400 meters north of the station. Find the rate in meters per minute in which the distance between train A and train B is changing at time t equals 2. So A is traveling east, B is traveling north. And they give us some information. They say that, and we want to know this distance. How is the distance changing? The hypotenuse, in other words. So this is train A, train B. Now, if I remember right, train A is 300 meters away from the station, and B, it says, is 400 meters away. So we have A squared plus B squared is equal to squared. I was thinking C. Let's call that C is equal to C squared. So 2A dA dt plus 2B dB dt is equal to 2C dC dt. Well, we have, let's see what we have. First of all, I can divide everything by 2. A is 300, B is 400. What is C then? The distance, 500, right? Yep. 3, 4, 5 right triangle. So A is 300. dA dt, the rate at which A is going at time t equals 2 is actually up here in the chart. So when time is 2, the rate is actually 100. So we actually know dA dt times 100. And I'm dividing everything by 2, so I'm ignoring the 2's. B is 400. Oh, and we need dB dt. That's a rate. And they gave us an equation for that, the velocity, the rate. So if we plug VB of 2, that's negative 20, plus 120, plus 25. So the 20s will cancel, and the rate is 125. And we know that C is 500. And we're trying to find out how fast they're going away from each other. So that's what we want to know. Well, if we divide everything by 100, that's 3 times 100 plus 4 times 125 equals 5 dC dt. So that makes smaller numbers to work with. Divide both sides by 100. So 300 plus, let's see, 400 and 4 quarters, that's 500. So dC dt is equal to 800 over 5. 1 160. And then, what is it? Meters per minute. Meters per minute. Because we ended up finding a rate. There we go. So related rates. There's a lot of things that can be asked about charts. That's one of them. All right, how we do? 1, average acceleration, negative 110 over 3. Good, we got that point. This, I kind of wrote it, except I wrote it in 2 different statements. And then conclusion, therefore, by the intermediate value theorem, there is a time t such that v of a of t is equal to negative 100 somewhere. And they're really looking for, what I would look for is, did you mention this? And of course, the rest of it has to make sense. 1 for the position expression. Hopefully I wrote that down. I don't know if did I? I may not have gotten it. Oh, I did. Ha! I got it. All right, I wrote that down. I did get that one. Trapezoidal sum, 1 point here, and then the final position at negative 150. Let x be trained as 2 implicit differentiation. So 2 to get this right, and then 1 for, then they jump down all the way to the answer, getting that 160. So there's the points for this one. All right, let's do another one. Oh, I love this one. This is one of my favorite problems ever. It is really a tour of calculus, big time. And notice that it's 4 ways to approximate f of 1.4. In A, we're going to approximate it. In B, we're going to estimate the value of f of 1.4. That's approximation. We're going to approximate, and finally, we're going to approximate it. And all 4 are different answers, but they're relatively close. All right, talk about the tour of calculus. Here we go. The function f is twice differentiable for x greater than 0 with f of 1 at 15, and the second derivative is 20. Values of f prime, the derivative of f, are given for selected values of x in the table above. Write an equation for the line tangent to the graph of f at x equals 1. Use this line to approximate f of 1.4. How long has it been since we wrote an equation of a tangent line? Been a day or two, right? So we have a point and a slope. That's how we write the equation of a tangent line. Well, we have the point. It's 115. And we have the slope when x is 1, 1/8, so 8. Y minus 15 is equal to 8 times x minus 1. So there's the equation of the tangent line. Now we need to plug 1.4 into this. So we get y minus 15 is equal to 8 times 0.4. So 15 plus 3.2. So 18.2 is the first approximation for f of 1.4 using a tangent line. And there's no way to really know what f of 1.4 actually is. We don't have a function. We only have a table. Use a midpoint Riemann sum with 2 subintervals of equal length and values from the table to approximate the integral of f prime of x from 1 to 1.4. So really this right here is talking about displacement. So that's not really position. That's not really a value. It's displacement. So what we need to do is start with 15. See how it starts with 1 there. So really we need 15 plus that to actually find the answer. And it says that. It says use the approximation that you found to estimate the value of f of 1.4. So we need 15 plus, and it says a midpoint Riemann sum with 2 subintervals. So that means we're going to go from 1 to 1.2 and 1.2 to 1.4 so that we have this middle value that we skip. So from 1 to 1.2 is actually 0.2, and then the midpoint is 10 down the middle. And then from 1.2 to 1.4, that's 0.2, and then the middle is 13. So 13. So there's going to be your approximation right there. So 15 plus 2, right? Yeah. Plus 2.6. So 19.6. Ooh, they might want that value actually on B. 1 for the midpoint. Oh yeah, 1 point for this. All right, well, I shouldn't do that. I should actually follow the instructions. So let me do this. This is how they want it to get the full credit. This is the midpoint Riemann sum, and that's 2 plus 2.6. That's 4.6. So you get a point for finding that value. I combined it too much. And then 15 plus 4.6 is 19.6. There, that's how we should write it to get full credit. I don't know what they would do if I wrote the first thing, if I left it. Use Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 1.4. Show the computation. So letter C. We're going to start with 115. We're going to start with the point that they give us. This one's a little tough. Well, let me do this. 2 equal steps to get to 1.4. So 1.2, 1.4. Now dx, the change in x is 0.2. Because you add 0.2, you add 0.2 to get to the third value there. We need to find dy. We need to find out how y changing. That's Euler's method. Well, usually we have dy dx is equal to 2y minus x. And then we'd multiply dx over, dy, minus x times dx. And this is the formula that we would use to use dy. We don't have that. We don't have an equation at all in this problem. So somehow we got to come up with dy. This is tricky. dy is equal to, we got to use what we have. Well, what we have is dx, first of all, is dx times, here's the real tricky part. Up in the chart, how can I write f prime? How can I rewrite that? What's that the same as? dy dx, right? So I actually have dy dx. So if we take dx times dy dx, we get dy, because they cancel out. That would be tough to come up with. Very tough. Well, the dx is 0.2, and for 1, the dy dx, or the derivative, is 8. So we need 0.2 times 8, 1.6, right? Yeah, 1.6. So this becomes 16.6, because we add on the 1.6, because that's how y changed. Well, then we do the same thing again. Now the dy is 0.2 times the derivative at 1.2. So the derivative at 1.2 is 12. Whoops. Times 12. So 2.4. So now our estimate is 19. So our first estimate was 18.2. Now we got 19.6 in B. Now we just have 19 with this method. All right, finally letter D, the last way to estimate. Oh, look what we have. Write the second degree Taylor polynomial. So a second degree Taylor polynomial will estimate the value of this function. Now, if they gave us more information, we could go to the 20th degree if we had enough information. So p sub 2 of x is equal to, how do we create a polynomial? What's the first step? F of 1, right? Because we're centered at 1. F of 1 is 15. Then what? Yeah, the first derivative, right? F prime. F prime of 1 is 8. So then we go plus 8 times x minus 1, because we're centered at 1. And then the second derivative. And they're like, well, how are we going to give them the second derivative? Well, let's just give them the second derivative. There we go. It's 20. That's why they gave you that. Plus 20 times x minus 1 squared over 2 factorial. So that's how we build a Taylor polynomial. Well, now we want p sub 2 of 1.4. 15 plus 8 times 0.4 plus 20 times 0.4 over 2 factorial, or over 2. 15 plus 3.2 plus 10 times 0.4. 20 divided by 2 is 10. So 18.2 plus 0.4 squared. Yeah, that's where I messed up. I'm like, that's not the answer. 0.4, so 0.16 over 2. 10 times 0.16. So 1.6, there we go. That's the right answer, 19.8. I knew something went wrong there. Thank you for the backup on that. There, yeah, hey. We went from all the way from writing tangent lines all the way to the end. Write the second degree Taylor polynomial. What a great problem. What a great tour of calculus. One for the tangent line, one for the approximation. One for this, one for that. One for midpoint Riemann sum. One for the fundamental theorem of calculus. Did I write that out? I did not. Oh, yeah, I kind of did. I shortcutted it. I probably shouldn't do that. 15 plus integral 1 to 1.4 f prime of x dx. If I don't write that, I don't think I'd have got the point. I think I missed that one. And then one for the answer, right there. Euler's method with 2 steps. So really, I just give you a point for this and a point for that. And then finally, one for the Taylor polynomial. That's either of these, I would imagine. And then one for the approximation, 19.8. All right, let's talk about multiple choice. Our good old friend, 1 over x squared plus something squared. So what are we looking for here? What are we thinking about? Inverse tangent, right? We're thinking about inverse tangent. So u is x over 3. Or another way to think about it is I want x to be 3u. So that when I plug 3u in for x, I get 9x squared so that they match. So if that was 25, I'd put a 5 down there. If that was 49, I'd put a 7 down there. I just want it to match eventually. So we can take the derivative of either one of these. How about we go 3 du is equal to dx, so that we can get rid of dx. So dx becomes 3 du. And x becomes 3u, so 9u squared. 9u squared plus 9. And now we're there. We've arrived. Because now we can factor out a 9. 3/9 is 1/3. 1 over u squared plus 1 du. So 1/3 inverse tangent of u, but u is x over 3 plus c. And then the next one is kind of revisiting an old friend. Find the intervals on which f of x is increasing and decreasing if f of x equals this. Notice this is an x to the third. We'll get back to that. But f prime of x is 3x squared plus 8x plus 5. So we're going to take the derivative, set it equal to 0. And factor it. 3x and x plus 5 plus 1. So the zeros are negative 5/3 and negative 1. And now we have to test those points. Negative 5/3, negative 1. And we got to find some values that fit. So how about negative 2? And this is an easy one. I love 0. But in between, we got to find something nice. And there are lots of choices, I would imagine. But the one that I would pick would be negative 4/3. Because negative 1 is negative 3/3, negative 4/3, negative 5/3. And what's nice about that is when you multiply negative 4/3 times 3, it's going to cancel out the 3. All right, let's go negative 2. Negative 6 plus 5 is negative, times a negative is a positive. Negative 4/3 times 3 is negative 4 plus 1 is positive. Negative 4/3 is slightly over 1. I mean, absolute value. So negative. Positive times a negative. So negative here. And then 0 is positive, positive. But I'll tell you what, I wouldn't have used a number line for this particular problem because I know what an x to the third looks like. I know that x to the thirds look like that. So here's a relative maximum. Here's a relative minimum somewhere. We just don't find the y values. So I wouldn't have done a number line for this. But you can. And if you have a function that you don't know what it looks like, absolutely use a number line. So increasing from negative infinity to negative 5/3, negative 1 to infinity, and decreasing from negative 5/3 to negative 1. All right, with your partner, try the last one. See what you come up with. It is a calculator problem. It is a calculator problem. If you're watching this at home, you're going to have to fast forward a little bit.
Okay, left, right, and south. You got the three
units of measurement.
It will overestimate because by decreasing. I know why it's an over. Well, it starts up here and then it goes down. And we're just doing one big giant.
I was thinking about the Travis.
Because it would be A prime. A prime.
I guess it would be A, because A of H.
Well, but we'd say that it's going down to the left. I'm in some overestimate. It's because A prime H is less than 0. Is that what you said? Degrees? I think so. The area in square feet of the horizon.
You do B.
B is the overestimate.
What is the units of measurement for A?
Just cubic feet. Oh, so we just do this. So this is area, and then like the derivative of area is
Horizontal cross section.
I think you do that from your.
We're not just looking at the
well, it gives you the area. Once you find the ball,
All right, you probably have A and B done. Let's take a look at that, and then maybe we can even talk about C. All right, you guys get 176.3? Take a look at that, 176.3. It's an overestimate, and I think I wrote over here, it's overestimate because it's a decreasing function with a left Riemann sum. This letter C can get a little tricky because we don't do too many of these. The area in square feet of the horizontal cross section. So the area of the cross section at height h feet is modeled by the function f, by that. Based on this model, find the volume of the tank, indicate units of measurement. What you're used to seeing is, let's say we have two functions like this, and I say, well, what's coming off the cross sections are squares. All right, so we have this and we have this. The cross sections are squares coming off of the xy plane. So you would integrate top minus bottom squared, dx. And that's how you're told to find volume of a cross-sectional area. Well, the cross-sectional area is not squares. It's that. Whatever that shape is the cross-sectional area at any h value. Go. See if that helps. It's not side squared. That's the area.
Oh, water is pumped in the tank and stuff? I forgot that. Okay, so we got H equals 5.
Well, let me ask you this.
And DH
If that's the way
is 0.26.
If I had this curve and this curve, and I had a square coming up right here, all right? Are we with me or not? Yes, okay. If I said that this side right here ended up at this particular moment in time, at this x value, whatever it is, this length was 2. What's the cross-sectional area? 4, right? Let's say over here, the length was 3. So the cross-sectional area there is 9. So the cross-sectional area at 3 happens to be whatever you get when you plug 3 in. Okay, so all we're doing is integrating from what? Based on my, I don't know. What are my indices? Oh, 0 to 10. 0 to 10 of this. That's it. That's it. Did you have it? Yeah, you had it. Good. Very good.
Take this derivative. And then we take that derivative and then we plug in these numbers that we have.
101. Okay. Last one's kind of tough. Because, I mean, it's tough because we don't do a lot of these. That's probably why it's tough more than anything. So let's read it. This one's been a struggle for everybody today, and I figured it would be. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26. What could I write for, let's say, when the height of the water is 5? What do you think I could write? H equals 5, right? For height, let's go H. What could I write for height is increasing at the rate of 0.26? Beautiful. Love it. DH dt. You must have a heck of a teacher. Oh, wait, that's me. All right. Now, use the model from part C. We'll talk about that in a minute. Find the rate at which the volume of the water is changing with respect to time. So what should I write there? dV dt is equal to question mark, right? That's what they're trying to find. All right. What did we say this was? What are we getting here? Volume, right? So volume, when we plug in H, is equal to this. So, how would that help us? What if I took the derivative of that? What would I write? Like we did here. No, not dV dt. dV dH, right? So dV dH, and we know the value of that. That was like the 101 value, right? Oh, no, not 101. That's the integral. So what is dv? What is the derivative of this? F of h, right? So dv dh is also f of h. All right. Believe it or not, we don't have all the numbers we need. We have all the pieces we need. Why do we have all the pieces? I see it. Okay, so this is what we want is equal to what? dv dh times dh dt. Evaluated when h is equal to 5. That's an important piece there. So now I need, what's dv? Oh, I have dh dt. It's times 0.26. How are we going to get dv dh? We plug it in for f. We plug it in for f. So you plug 5 in for f, multiply it times 0.26, you got it. That's a rough one. That really is. I'm not going to pretend it isn't. Not going to pretend it isn't. And we can even cheat and see what the answer is. Do they give us a, they don't give us the actual value. So try to get 1.694. I'm going to shut this off. Then I'll show that again.